Okay, welcome back, everyone. Our second speaker is Oscar Bandtlow, who will talk about explicit resolvent bounds for transfer operators.
Okay, thank you very much, Julia, for this introduction. And of course, thank you very much for the organizers, Stefano Garattolo and Sébastien Guezel, and René Chassot, I suppose, is also one of the organizers who is not here. Thank you very much for giving me the chance to talk here at this really, really interesting meeting. What I'm going to talk about is resolvent bounds for transfer operators. Well, we probably all know what a transfer operator is. And if you have ever done any work with transfer operators, in particular with the spectral theory of transfer operators, you know that whenever you try to get error estimates or calculate spectra with some confidence, what you need to do is you need to somehow bound the norm of the resolvent of the transfer operator in the vicinity of the spectrum. Okay, so this is something you need to do in some form. And I'm going to talk about one particular method that applies to transfer operators that arise in the setup of holomorphic systems. So yesterday, Julia gave a talk where she talked in some detail about the setup where you have a holomorphic or analytic dynamical system. And in this case, you can find spaces on which the transfer operator has amazingly good properties. Typically, they are compact. And in this case, you have some hope of actually trying to find error bounds for spectral approximations. In particular, you get a priori error bounds for spectral approximations. Yesterday, Isaiah gave a very, very nice talk about how to get a posteriori error bounds that go back to work of Stefanos. Here, I'm going to talk about a priori error bounds. What are a priori error bounds? These are bounds that you get before even turning on your computer. No? So before you even click the button, you know how good, or in my case, bad, your approximation is going to be. Good. So this is a rough outline. Let me start. So this is more or less what I already said, but this sets the scene. It's a very, very high level view on transfer operators. So this is the story. Imagine we have some dynamical system T. And in my talk, typically I would assume T to be an analytic map with very, very high analytic map, which is also expanding so that transfer operator methods actually come to into bearing. But for the moment, this is all very general. So I suppose I have a dynamical system. Typically, it should be expanding or hyperbolic. And imagine I have a nice transfer operator acting on some suitably chosen Banach space, X to X. And what we want to do is, for some reason, we are interested in calculating the spectra of these operators, because spectra of transfer operators tell you something about the invariant measures, about the relaxation times to equilibrium. They even tell you something about invariance of the dynamical system. They allow you to calculate Hausdorff dimensions and many, many beautiful things. So there is some interest in calculating spectral data of these operators. And I suppose since you're here, I don't need to convince you that this is actually the case. So typically, this operator is an infinite dimensional operator, as you know. And how do you calculate spectra of full-blown infinite dimensional operators? Well, one way of doing this is you manufacture some discretizations. And typically, these are finite rank discretizations. And you suppose that these finite rank discretizations converge in some sense to the original operator. And then there's the hope that the spectral data of these guys, which for this talk I assume are completely given. Of course, if you work in numerical linear algebra, then you would say this is lunacy. This may not even be possible, but I assume that in principle, you can calculate all the eigenvalues and eigenvectors of a 100,000 times 100,000 matrix if necessary. Again, this may not be the case, but I'm going to comment on this later on. So I hope, I hope that this spectral data of my matrices somehow converge to the spectral data of my full-blown operator. And this is an idea that has a very, very long history, probably goes back to this famous approach of Ulam from 1960, who proposed, first of all, the idea of looking at the Frobenius-Perron operator to study invariant measures of expanding dynamical systems. And he also suggested a way of how to calculate them. So this is, in a sense, the granddaddy of all these approaches. And ever since then, there have been numerous other ways in which to make sense of these two lines over here. Many, many people in the audience have actually worked on this. And I had a long line of people who worked on this slide. And I removed it just now because I got cold feet, because I thought if I don't mention anybody, they're going to be very grumpy with me. So maybe I did the wrong thing. But anyway, so this is just to say the usual waiver. Many, many people, many of whom are in the audience, have worked on this and contributed to this. Enterprise. Now, I'm going to focus on the analytic setup. So this is something Julia has talked about yesterday, and there's going to be some other talks. Suppose the underlying system T is analytic. For example, you could take the doubling map on the circle, or the squaring map on the circle. So this is a good example of an expanding analytic dynamical system. Or you can take Anosov maps on the torus, for example, the cap map or its perturbation. So these are perfectly good examples to think of in this situation. And there's a way in this situation where you can choose a space, a Banach space X, in such a way that the corresponding transfer operator is very compact. So very is not a mathematical term. Let me try and make sense of this. So what I mean by this is that this operator certainly is compact, but it can be approximated sufficiently fast by finite rank operators. And in order to measure the speed with which operators can be approximated by finite rank operators, it's convenient to introduce these objects over here. So these are probably numbers you may or may not know. So suppose, so this is now completely general, it has nothing to do with transfer operators anymore. Suppose you have a Banach space and a bounded operator from X to X. In fact, it doesn't have to be from X to X, and it can also go to another space. It still makes sense, but for the moment, I just think of A as a bounded endomorphism. And you take your favorite integer n, then you can define the so-called nth approximation number of the operator A. And how is that defined? Well, you look at your operator A, you subtract an operator of finite rank, in fact, of rank less than k. And this is a typo on my slide. Never good to make slides at 10 o'clock in the evening. So this k should be an n. So the kth, or the nth approximation number, is the inf over all differences between A and F, where F has rank n. Okay. So this is the best approximation of A by operators of rank less than n. So these numbers come up in the in analysis of compact operators. In particular, if the nth approximation number of an operator goes to 0, then the operator is compact. The converse is not true unless you are in a particular nice setup. For example, if X is a Hilbert space, then the converse is true. So an operator is compact if and only if these approximation numbers converge to 0. And also something relate them to stuff that may be more familiar to you. So this nth approximation number as defined over here is also equal to the nth singular value of the operator A, which means you take A star. This is, if A is compact, this is the eigenvalues are discrete, so you can order them by decreasing modulus, and then the square root of this is the nth singular value, and in the Hilbert space setting, this coincides with the nth approximation number. Okay, good. Right, so these numbers quantify how compact an operator is, and what I wanted to say in this first box over here is that if your system is analytic, then you can choose a space X in such a way that you can approximate the transfer operator, in principle at least, at a certain speed by operators of a prescribed rank. Okay, let me quantify this. So what comes out of the analysis of all this is the following. Again, let's assume the underlying system is hyperbolic, so that transfer operators actually make sense. And we also assume it's analytic, and I assume that we are in the D-dimensional setting. So, for example, we could be on the 2 torus, in which case D would be equal to 2. So the fact is that in this situation, you can choose your Banach space X as a space of analytic functions or holomorphic functions. Typically, these will be functions that are holomorphic on a neighborhood of the domain where the map is analytic. And there's a whole zoo of spaces you can use. In the expanding case, there's a lot of flexibility. You can choose Hardy spaces or Bergman spaces. I don't want to go into details. The only thing I'm going to need is the following thing. You can choose your space X in such a way that the nth approximation number of your operator has a certain rate of decay. So what is written over here is a stretched exponential decay. This 1 over d is the stretching. In particular, if you're in the one-dimensional setting, so for example, if you talk about analytic interval maps or circle maps, then d is equal to 1, then you get exponential decay. How do you get these estimates? So where do they come from? Ultimately, this is some sort of a glorified Cauchy theorem, bounding the norm of the derivative of an analytic function. This is ultimately what is behind it. And how do you prove these results? You typically prove this by not studying the full operator, but you only study a simpler example, namely an embedding operator between two domains. And you use the fact that the transfer operator in nice enough situations factors and can be written as a bounded operator and an embedding operator. And the embedding operator, can be written in a particularly simple form. So this is more or less how you get these estimates. Julia explained this in her talk yesterday. So I think so in a sense, these results have been lurking about in the literature. If you could go back to the famous paper of Weil from '76, where he doesn't really talk about singular values, but if you look at the proof he gives, it could be adapted and phrase it. You have to do quite some bending to do this, but it's in a sense it's lurking there already. But it's written in the expanding case. This is written up in an old paper of mine and Oliver Jenkinson, and there's a recent, so this deals with the expanding case, and the Anosov case in dimension 2 is dealt in this recent paper with Julia and Wolfram. And there's a really, really beautiful paper by Malot Jessica, also from 22, which deals with analytic Anosov diffeomorphism in general and gives this estimate. Okay, so that's the first fact. If your map T is very, very nice, that is analytic, then you can arrange it in such a way that you can calculate, can give an upper bound for the approximation numbers of your transfer operator. Okay, good. First fact. Second fact. So this bound here says there exist finite rank operators such that you can approximate L at the speed. In practice, the way you prove this also gives you a concrete way of finding a discretization scheme that realizes the speed. Often the speed is not realized completely. You have to give way a little bit. So often the constant, there's another constant here. That's why it's called A prime. So this convergence may be not as good as the original one, but you still get the still get close to the optimal bound, the desired bound, and at least the stretching factor is the same. So what I wanted to say is, in practice, you can often find finite rank operators or operators of rank k in such a way that the distance operator norm relative to your underlying space X is bounded by this stretched exponential. Okay. Sorry. Yeah, I do apologize. That's another typo. Very good. Thank you very much for spotting this. This k should be n. K should be n, and k has rank k. Yeah. Okay, and there are some papers where this discretization scheme is actually written down explicitly. For example, there's a paper of Caroline from 2019 in dimension 1, where she explains that some sort of a Gajokin method or a Lagrange-Chebyshev method converges at this rate. And there's also a preprint by myself and Julia. And there's some other papers, probably more than I've written over here. I do apologize if I missed some by Paulina and Caroline, and also by Julia and Mark using something like this. Okay, and the third fact is that often X can be chosen to be a Hilbert space. Okay, so this doesn't, from the dynamical perspective, this doesn't really look like very much, because in dynamics you never worry too much whether you are in a Hilbert space or not. Often, in fact, the good spaces are not the Hilbert spaces, but they're typically Banach spaces. So the most natural space on which transfer operators live, or Frobenius-Brodin operators live, are L1 spaces. But for what I'm going to say, it is important that X is a Hilbert space. So for these resolvent bounds, it turns out that it makes a big difference whether you live in a Hilbert space or in a Banach space. Basically, life for a spectral theorist is just better in a Hilbert space. So that's what I'm going to talk about in a second. Okay, so before I go into the gory details of resolvent estimates, let me give you a first consequence. So because we have norm convergence of the approximants to my full operator L, so this is the operator norm relative to the underlying space X. So this is the operator norm as an operator from X to X. Because of this strong convergence, because of uniform convergence, you know, and the fact that L is compact, you know that spectral data of LK does converge to spectral data of L. So in particular, all the eigenvalues converge and all the eigenvectors, also the general eigenvectors converge. So this standard perturbation theory gives you this. If you're not in the elliptic setting, where it's hopeless to get convergence like this, where you don't get uniform convergence, where you have to do with something weaker, often you have a convergence uniform relative to some weak and strong norm, and the operator L is no longer compact, but only quasi-compact, then you still get some convergence. You can use this beautiful theorem of Keller and Liverani that gives you convergence of the discrete part of the spectrum. Okay, but here I'm using the fact that we are in this beautiful, or not beautiful, but in this very, very good setting where you have uniform convergence. So now in practice, this is a conference about validated numerics. You can't go to the limit, you have to stop somewhere. Okay, so in principle, you have to, for some reason, you have to stop at a finite n. N may be a 1,000 times 1,000 matrix, or I've also seen people do something larger than that. The question is then, you have this matrix of size n times n. You can find its eigenvalues and eigenvectors. How close is that to the eigendata of the true transfer operator you want to approximate? Okay, so this is the question I want to address now. And at the moment, I haven't really quantified what I mean by closeness of spectral data. So let me quantify this. So the quantity I'm going to focus on is the Hausdorff distance. You probably all know this, but just in case you don't know. So this is a way of quantifying closeness of spectra of two operators, in in fact, it's just quantifying closeness of two compact sets in the complex plane. How does this work? So I imagine you have two, let me just run through this definition. This is probably not the best, but it's the shortest. So you take two closed sets, let's call them sigma and sigma prime, and let's suppose Z is an arbitrary point in the complex plane. Then I use this Z sigma for the distance of the point Z to the set sigma. This is going to come up later on as well. And then I use this hat dist for the supremum of all the distances from points in sigma to points in sigma prime. So I call this dist hat. And the Hausdorff distance of the two sets sigma and sigma prime is simply the max of the two hatted distances where I swap sigma and sigma prime around. So this thing here is not symmetric, and it's not, and for that reason, it's not a metric, but this thing is now symmetric. And it also turns out to be a complete metric on the set of compact subsets of the complex plane. Okay, if you didn't like this definition, maybe another way of thinking of this is if you have two sets, sigma and sigma prime, if the Hausdorff distance of these two sets is, say, epsilon, then this means that every point in sigma prime is within epsilon, an epsilon distance of points in sigma, and every point in sigma is within an epsilon distance of a point in sigma prime. Okay, so this is one way of thinking about this. And in particular, the Hausdorff distance is 0 if and only if the two sets coincide. Okie doke. So let me rephrase what I'm going to tell you about. If you have two compact operators, find explicitly computable upper bounds for the Hausdorff distance of the spectra of these two operators. And in my case, I'm going to focus on A being a transfer operator arising from some analytic dynamical system with good spectral properties, and B may be one of its approximates. Okay, good. So when I first started thinking about this, I came across the following finite dimensional prototype of this problem. So before you go to infinite dimensions, you want to do something in finite dimensions. And this is what is written over here. So here's the finite dimensional prototype of the results I'm going to present to you. So this is an old result going back to the 50s and 60s, and there's an optimal version from the 80s. So what does it say? So this is something about matrices. So suppose n is a natural number and Cn, okay, so n is a natural number. Then the claim is there's a sequence of numbers Cn. That's for any n times n matrices A and B, we can bound the Hausdorff distance of the two spectra of A and B. That is simply the set of eigenvalues of A and B can be bounded by this expression over here. Okay, let's look at this expression. What does it contain? First of all, it contains the difference in operator norm of A and B raised to some power 1 over n, so where n is the size of the matrices. Then we have this constant m over here, which is simply the maximum of the operator norms of the two matrices. And there's this number Cn over here. Okay, so the first results, so Ostrovsky proved this using determinants. So he basically said he gave a bound for the distance, the Hausdorff distance of the zeros of two polynomials. And then he was then able to relate it to the spectra. And Henrizi used a different approach, which actually generalizes to infinite dimensions. And their method, however, only gives that this constant over here is bounded by n, so it's not constant. In 85, Ludwig Elsner gave the optimal bound, but only provided that this is the spectral norm. Okay, so what is the spectral norm? The spectral norm is the operator norm when you think of the underlying n-dimensional space as a Hilbert space. Okay, so this is simply the usual L2 operator norm. And in this case, it is important because if this these two bars here designate any arbitrary matrix norm, then this constant 1 need not be true. In fact, you can show that Cn, if the underlying space is not a Hilbert space, then Cn is typically greater than 1. But recently it was proved that it's still bounded as n goes to infinity. Okay, and at the moment there's a hunt for the best constant going on, as often in mathematics. Okay, so this is the story about, first of all, Hilbert space setting is better than Banach space setting. This is what this says. And also something I want to comment on is this 1 over n. So first of all, this the bound Cn is equal to 1 is optimal. You can find matrices A and B that realize this. And this 1 over n here is unavoidable. This arises because you can have Jordan blocks. And the Jordan blocks, so what is the same thing? The resolvent of the operator has a pole of order n. And this makes it unavoidable to have this power 1 over n over here. So you can have eigenvalues that split and behave in exactly this behavior. If you don't have Jordan blocks, you lose the 1 over n constant. You can do better, but at the moment it's unknown. So in principle, it should be possible to prove something. So in principle, what should be here is the size of the largest Jordan blocks of both operators, or in other words, the order of the largest pole that occurs for the resolvent of the two operators A and B. So this is something you should be able to put here. However, I'm not aware of any proof that allows you to show that this is the case without with a universal constant. Your constant may, in this case, or may in this case, depend on the two operators A and B. Okay, any other questions? One more comment. You would think that this lends itself to generalization to infinite dimensions. Okay, you just take your compact operator, you approximate it by finite rank operators, and then use this. But as you can see, this 1 over n kills it, because as n goes to infinity, this goes to 0. So you lose the dependence on the difference in operator norm, which is what you want in the end. Okay. Good. So let me now tell you how to generalize this to infinite dimensions in both the Hilbert and the Banach space setting. So the idea, okay, so what is nice about this is, I thought, okay, in principle, for transfer operators, you can calculate all this data in principle, okay? You can often, exactly what the difference in operator norm is between your transfer operator and your approximant. And all the other numbers you can also calculate in principle. Okay, good. So let me show you how to get estimates of this type in infinite dimensions. Turns out that it's important to have resolvent estimates of a particular type. So what are these resolvent estimates of a particular type? They look like this, So suppose you have a bounded operator A, and suppose you know that for all z in the resolvent set of your operator, you know something about the norm of the resolvent. Okay, so the resolvent is typically is a holomorphic function on the resolvent set, and if A is compact, the only singularities are poles. So what happens as you approach a singularity is that the norm should blow up, and if you can control the blow up near a pole in this fashion, then you are in business. So what is this fashion I'm talking about? I assume that I have a function g defined in the positive reals that bounds the blow up in the following sense. It bounds the blow up in terms of the 1 over the distance of my point z to the spectrum of A. Okay, so I assume that I have a bound like this, and I'm allowed to assume that this function depends on my operator A only. So a good example where this is the case is if you're in a Hilbert space and your operator A is normal, then it follows from general nonsense that the operator norm of the resolvent of my normal operator is simply 1 over the distance of Z to the spectrum of A, okay? In particular, the only type of singularity that a normal operator can have is a pole type singularity. Nothing worse can happen. And this more or less accounts for the good properties of normal operators. Okay, so in this case, my GA would be the function, would be the identity. So GX would be simply X. In general, you have to contend with something worse. And I'm going to tell you how to get these functions later on. For the moment, I'm going to tell you why, if you know such a function, you can calculate bounds, explicit bounds for the Hausdorff distance of the spectra of 2 operators. And this goes back to something that Isai explained yesterday. It's to do with the householder approach to proving Gershgorin's circle theorem. But in the numerical linear algebra community, it goes by a different name. It's known as the Bauer-Fieke lemma, which is from 60, which is around the same time as the householder proof appeared. Okay, so here's how it works. So this is not how Bauer and Fieke wrote it down. They had a slightly different version, and also they were only interested in finite dimensions, but it's easy to extract their argument, make it work for an arbitrary Banach space. So this thing here works for any old bounded operator on a Banach space. So let's suppose we have an increasing surjective function from the positive reals to the positive reals, such that for all Z in the resolvent set of my operator A, we have this bound on the growth of the resolvents. So I suppose I have this function, and it only depends on 1 over the distance to Z to the sigma A. If this is the case, then for any old other bounded operator, B from my Banach space X to X, every spectral point of B is within a calculatable distance to the spectrum of sigma of A. And how do you calculate this number over here? So it only depends on the difference in operator norm of A and B. And it depends on this function H of A. And how do you find this function H of A? It is given by this function, okay? So G is a surjection. GA inverse is the inverse function of G of A. And HA of X is simply the reciprocal of GA of X evaluated at reciprocal of X. Okay, good. So every talk, I was told at some stage, has to contain a joke and a proof, but they don't necessarily have to be the same. So let me now give you a proof of this result. Oops, sorry. So here's the proof of the Bauer-Fieke lemma. So here's how the Bauer-Fieke lemma works. And if you look at this, you will see it looks suspiciously like the argument that Isaiah gave yesterday. So let's write B minus A for the difference of B and A. Let's call it E for error. And I claim that if Z belongs to the spectrum of B, but not to the spectrum of A, then 1 over E, and I presume you have to assume that this is non-zero, is less than or equal to the resolvent of A at Z, the norm of the resolvent of Z at A. So how do you do this? This is here you can see this is the basic perturbation theory. All of perturbation theory works like this. How do you do it? Suppose that Z belongs does not belong to belongs to the spectrum of B, but not to the spectrum of A. So what I'm trying to do here is I'm going to prove the contrapositive, okay? So I'm not going to show this, I'm going to show the reverse. So let's suppose that Z has this property, and suppose to the contrary that this inequality here is violated. How do I violate this inequality? Well, I assume that norm of E times the norm of the resolvent is strictly less than 1. So this is the reverse of this inequality. If this is the case, then I do the standard perturbation theory factorization. I write zi minus b, the resolvent of b, in terms of the resolvent of a, using the fact that I can invert zi minus a, and here I have my e in it, okay? So if I multiply this back in, I get z minus a minus e, but e is b minus a, so this is in fact zi minus b. Okay, so this line is correct. And now this assumption here kicks in. If this guy over here has norm less than 1, then by Neumann's estimate, this guy 1 minus zi minus a inverse e is invertible. So this guy over here is invertible, but this guy is also invertible. So zi minus b must be invertible. So z must be in the resolvent set of b, and hence cannot be in the spectrum of b, which is the desired contradiction. Okay. And if you look at this, this is more or less the same that the proof that Isaiah gave yesterday, for a slightly different setup. Okay, so how does the claim imply the Bauer-Fieke argument? So suppose Z belongs to the spectrum of B, but not to the spectrum of A. Then, by the claim we just proved, the reciprocal of the norm of E must be less than the resolvent of Z at A inverse. But by hypothesis, we assume that we have this universal, not this universal function, that we have this function g of A that only depends on 1 over the distance of Z to the spectrum of A. And now we use the fact that GA is invertible. It's an increasing surjection. So we have an inverse. We can flip it over because it's monetarily increasing and preserves this inequality. So we get J inverse of 1 over the error of, that is B minus A, must be 1 over the distance of Z to the spectrum of A. And then I rearrange, I get that the distance of Z to the spectrum of A is less than this 1 over GA inverse E reciprocal, which is now my magic function H of A. Okay, so this is how easy it is to prove this Bauer-Fieke lemma. And of course, I don't need to make the assumption that Z is not in the spectrum of A, because if Z is in the spectrum of A, this number here is 0 anyway, so I can forget this. So the whole thing now says if Z belongs to the spectrum of B, then the distance of this point, the spectral point of B to the spectrum of A, must be given by this number over here, okay? H of A times norm of A minus B. And the particular consequence of this is, remember, if A and B are normal, then my function G was simply the identity. So in this case, the inverse is also the identity. So in this case, you get that this function H of A is actually the identity as well. And we get the result that if A and B are two normal operators, then the Hausdorff distance of the two spectra is simply bounded by the difference in operator norm. Okay. But this is very, very peculiar to normal operators. In general, you cannot hope for anything like this. So let me now explain to you how you get these type of estimates. So how does this work? So here is a result that goes back to some work I did with my former PhD student, Aisha Guven, in 2015. So suppose A is a trace class operator. So now we are firmly in the Hilbert space setting. X is a Hilbert space. And I suppose that the singular values of A are summable. Okay, operators of this type are called trace class operators. And for trace class operators, you get this explicit estimate for the resolvent of my trace class operator that is expressible purely in terms of the distance of Z to the spectrum of A and the singular values of A. So this is my function G of A. As you can see, it contains the singular values of A and only the distance of Z to the spectrum of A. So this function here satisfies the properties, the hypothesis of the Bauer-Fieke argument. So if you've ever seen anything like this before, you may be surprised. I don't know, I'm not sure how surprised you are at this after half an hour into a talk, but let me try to explain to you how you get this result. This follows from this classical estimate. And what is classical is always something that the speaker knows, but not necessarily anybody else. But this is why it's called classic. If you've never seen this before, let me try and walk you through it. Let's take a trace class operator A, and let's suppose that -1 is not in the spectrum of A, so that 1 plus A has an inverse. So then it turns out you can bound the operator norm as an operator on a Hilbert space by this expression over here. So here you've got the 1 plus the singular values of A. And by the way, this product here converges because the singular values are summable. So this is where this hypothesis of summability comes in. Otherwise, I can't, this infinite product may not exist. Okay, so this is where summability or the trace class assumption comes in. And what you have down here is nothing but the determinant of the operator 1 plus A. So down here, I have determinant of I plus A. Okay, and how do you get this? So this is something that, again, is also classical. I'm not sure whether they've seen this before. This is a bound for an n times n matrix. If you have an n times n matrix, then it's the spectral norm of its inverse is equal to the product of the first n minus the first, well, all the singular values apart from the last one, divided by the determinant. And now I have to ask the chair when I started. 25. Okay, brilliant. Then I can, but there's 10 minutes of discussion, so I have 10 minutes left, no? Okay, that's good. So then I can give you another proof for free. So let me try and prove this for you using the blackboard. So A inverse for a matrix. So suppose A is an n times n matrix. N times n. Okay, so A inverse spectral norm is, as you may know, equal to 1 over the smallest singular value of A. Don't believe this. This follows from the C star equality. If you wish, we can write this as square root of A star inverse. The A star is now a positive matrix. So the norm of this must be 1 over the smallest, or is the largest eigenvalue of A inverse, but this is 1 over the smallest eigenvalue of the positive matrix A star, and this is how you get this. Okay, anyway, not sure whether you believe this or not. Anyway, this is a known fact. And how do you get this? Well, this is very easy. You simply write, you expand by S to A dot Sn minus 1 to A. You multiply upstairs and downstairs. So downstairs, you get S1A, S2A, dot, now all the way up to Sn of A. Okay, that's the product of the n singular values. But this is, as a little thought shows, nothing but the determinant of A modulus. Okay, so these guys are the determinant of the modulus. Again, it's easy to derive. You could also think of this as some sort of Weil inequality. So if you wish, this is a Weil. This is a relation between the eigenvalues of A and the singular values. And I'm saying this because I'm going to later talk about the Banach space case where this Weil inequality will come in. Okay, good. So now I hope you believe this. If you have this, you may find it sort of easy to believe that you get this, or you simply replace A by 1 plus A, and then you have to do some gymnastics to get to the infinite dimensional setup. So here you have Sn I plus A, but it follows from the definition of the singular values that the nth, or in fact, the approximation numbers. So the nth approximation number of I plus A is less than 1 plus the nth approximation number of A. So this is how you get this expression over here. And from there, how do you get to there? Well, this is not so obvious. You have to do something else. In particular, you have to find lower bounds for determinants, okay? So if you put in Z over here, Z, you get this over here, so you almost get the resolvent, then you still have the problem that you have 1 over the determinant of a trace class operator. And if you want to get an upper bound, you have to find lower bounds for the determinant of a trace class operator. And this is something where part of the work went in. It's not particularly difficult, but you still have to sit down and do a couple of inequalities. So the square here, actually, if you want about the square comes from a lower bound for the determinant of a matrix. Okay, good. So you may believe this or not. The thing is that in principle, this is something this data you can calculate for a transfer operator. So for a transfer operator, you know these numbers, or at least you have an upper bound. And that's it. That's the only thing you need to know. Okay. Yeah, okay, let me comment on some of the intricacies of this later on. So this became a sporting interest for me. I wanted to know if this is actually true for Banach space cases, and it turns out it is true, but it's significantly more complicated to prove. So here's a very recent result. So this is the analog of the previous result, but now I'm assuming that X is any Banach space. And I still need the summability condition for the approximation numbers. Then you get an estimate of this type. The only difference is that instead of the 2, I now have a 4 here, which is unavoidable. And I also have a constant C floating around. But this constant C is universal. It doesn't depend on A or my Banach space. It's bounded by 2 Euler number square root. Okay. Anyway, how do you prove this? You can't use any of this. You have to do something completely different. You have to use some very, very powerful Weil inequality for the eigenvalues of operators in a Banach space. So there was a long hunt how to get optimal Weil inequalities, and there was a breakthrough due to Peach in the 80s. And the idea is that you, instead of having the usual Weil inequality, you have a Weil inequality with doubled sequences, and the doubling gives you the 4 over here. It's probably all incomprehensible, but anyway, gives you an idea where stuff comes from. Okay, good. Anyway, in practice, you probably don't need this because, as I said, you can often choose for your space a Hilbert space for transfer operators. Okay, so let me now come to a punchline. Let me apply this to transfer operators of hyperbolic analytic maps. So suppose we have a discretization, and this discretization suffers from the same problem that Sébastien already pointed out earlier on. This N should be a K. So LK is a discretization of rank K with the property that the distance and operator norm in your chosen space adapted to the system decays stretched exponentially in K at a certain rate. And I also assume, so this is, you usually get this for free. This is nothing you have to worry about, that you have an explicit bound for the transfer operator. So you know that the singular values of the transfer operator are bounded by a stretched exponential. I told you that this is always the case. And often the way you construct these discretizations, typically you can obtain them as like a Yorkin approximation, in which case this uniform bound in K with the same N and the same constant you get almost for free. Okay, so I assume that both my transfer operator and my discretizations are bounded, the singular values are bounded by this decreasing exponential. And I can then plug this into I can then calculate the function GA in this case, or the corresponding resolvent bounds. And I can calculate how fast the function G grows at infinity. So how fast the function grows at infinity depends on how fast the singular values decay to 0. And this in turn depends, if you look at the definition of this function h of a, tells you how fast the function that gives you an upper bound for the Hausdorff distance decays to 0 at 0, which is the interesting bit. So what I'm claiming now is in this setup, you can find an explicitly computable function, capital H, on the positive reals that gives you an explicitly computable upper bound for the Hausdorff distance of the spectra. And there's also a bracket missing here. This should be sigma lambda, sigma L, sigma LK. I do apologize. Times this constant here, times this universal function. And here you only have the difference in operator norm, for which you have upper bounds. And what I claim over here is that this function, which is known explicitly, is known completely explicitly. You can calculate everything explicitly in the given setup. So this hypothetical error decays stretched exponentially. But here you have d times d plus 1 in the stretching factor. So d is the dimension of the system. In particular, if d is equal to 1, you get, unfortunately, 1 over 2 as my stretching factor. Okay, and you're telling me that it's time to stop, I suppose. So let me wrap up with the following thing. I was fortunate enough to come to Pisa on the feast day of San Ranieri, the patron saint, and which is 17th of June. And there's a palio, a race of neighborhoods, which you can find in many other Italian cities. And here in Pisa, it's done with boats. And I was able to observe this race, and I can report that this year the Reds, which is San Martino, I suppose, came in first. And I'm showing you this because it was really nerve-wracking. First of all, the Barca Rossa came, and then the greens followed, and then the blue came, and then it was nothing, and nothing, and nothing, and nothing, and then suddenly the yellow boat arrived. And I'm still, I need to know whether my estimates are in the yellow boat or are in the red boat. Thank you very much for giving me the chance to talk about this.
Questions for Oscar?
I was going to ask. So I'm wondering so I guess I'm wondering about, so this bound is kind of works for all of the whole spectrum uniformly, yes. Right? So I guess usually people, when you're trying to estimate these things, maybe you're interested in an eigenvalue that's kind of on the periphery, and you have some garbage in the middle of, like, often it's just like there's some stuff in a small ball that's just, because it's really unstable there. So can you get better results on the distance to your spectrum if you have, like, if Z is not is close to the unit?
Exactly the right question. Exactly the question you should ask. Yes, this is what you should do. So so the problem with these estimates is that they are poor because you also allowed to approximate the 0, which is in the spectrum of any compact operator, and there you can have the resolvent can blow up quite fast. So at all the other spectral points, the resolvent is only a pole, but at 0 it will blow up very, very fast. And these estimates, because they're uniform, take this worst case scenario into account. So you should be able to get better estimates by restricting Z to a disk, to the exterior of a disk centered 0. And what you have to do is you have to, again, find analogs of these lower bounds for this. And I I think I'm very close to this, but I thought I would get it for this conference, but I didn't quite manage to do it. So yes, good question. I'm thinking about this, and I think there is some hope that this may improve these bounds. And ultimately, you will get something that bounds that decay like 1 over n for a certain n, and the n may depend on your radius and the singular value asymptotics of your operator.
So 1 on n being,
sorry,
like 1 on n as in,
yeah, for the
as
the
like
1
G
over n,
is 1
for
on
the n, the thing is n is now a variable. N could be very large or could be very small. It will depend on what part of the spectrum you're trying to approximate, and also on the asymptotics of the singular values of your transfer operator.
More questions?
So I have thank you for your talk. It was really nice. I have a really stupid question that is,
Yeah, only
so,
stupid answers.
so when you write that you define this Sn or Sn of a, you define this as the inf over the f of finite rank, okay? And these are k by k matrices, we could think. So in principle, this could be a minimum.
This could be?
This could be a minimum. Maybe we can try to find this, think of, I don't know, try to find the best approximant. Do you think it's possible to find the best finite rank approximant?
So there's a whole industry devoted to this. So there are people who take some Sobolev space and take another Sobolev space, and they're only trying to calculate the embeddings of the singular value asymptotics for these embeddings. And this already is very, very, very complicated. I mean, people write lengthy papers just devoted to this. And these are simple operators, no? These are simply more or less the identity restricted to 2 different spaces. And there it's already very, very complicated to find the exact asymptotics. So in general, I think for an arbitrary transfer operator, I doubt that, I mean, you can probably do it. It could be a sporting interest. But I doubt, first of all, I doubt you'll be able to do it. And secondly, I doubt that this is the bottleneck in calculating, finding error estimates.
Thank you.
More questions? Well, if not, let's thank Oscar again for a very nice talk.
Welcome back, everyone. Welcome for the afternoon session. We will start with Mark Pollicott. He will talk about estimates on Lyapunov exponents via the pressure function.
Thank you very much. Oh, a bit loud. Thank you very much. Okay, let me begin by thanking the organizers for their kindness and inviting me and to give a talk. And let me say it's a pleasure to be back in Pisa. And some of you know I don't usually work on computer-assisted proofs, and it occurred to me that the nearest I got to doing a computer-assisted proof was about 10 centimeters. I used to have the office next door to Oscar Lanford. He was much better at that kind of stuff. What else did I write down? Oh, yeah. So I should say that entering into the spirit of this meeting, I'm going to give a Blackboard talk. There'll be no computer talk involved in this, this particular presentation. And my plan, as illustrated on this Blackboard, is to say as little as possible slowly. So this shouldn't be too much of a strain, at least not for me. And to compensate the audience, I'm giving out chocolate. So I will ask Sebastian to do the courtesy. Now, the airport, I always buy the biggest box I can find in anticipation I'll have an enormous audience. Somehow it never quite goes that way. So help yourself to 1 or 2 or 3 or 4 pieces. Okay. And in fact, that's everything on my script. So the rest of it will be the talk. So as it says on the board, my aim is to talk about Lyapunov exponents. And by that, I mean just a number associated to some simple dynamics. But I'm only going to consider the simplest possible settings. Anything complicated, I always avoid. And the approach to getting a handle on the Lyapunov exponents is going to be the pressure function, which I realized was not a good thing to put in the title because it's not very evocative, but it will be defined in due course if you don't know what it is. And if you know what it is, you won't be surprised. So my approach is to look at this thing called the pressure function. And why am I interested in this? Well, I'd like to get some numbers out at the end. And the numbers would be, for example, Lyapunov exponents associated to some measure, absolutely continuous invariant measure, for an expanding map on a circle, something like that. Or maybe even random products of matrices, something in that line, but always in the simplest possible setting. So there's two contexts. One will be maps, which will take most of the talk. And if I'm lucky, I won't get as far as the random matrix products, but if I do, that will be a smaller portion of the talk. Okay, so in the interests of economy, I have written down the first half page of my notes. So I'm interested in the setting of just maps. And these are expanding maps, for example, on a circle, or possibly on an interval. For those of you that like pictures of circles, here is a picture of a circle. And there is a picture of a map, x, t of x. And so the circle here is denoted by S1, no particular reason. And I want the map to be at least C2, because I'm actually interested in absolutely continuous invariant measures, and that's a good thing to assume if you're interested in such things. And I'll assume that the degree is greater than or equal to 2. Otherwise, it's kind of difficult to have expanding maps on the circle. And I'll assume that they are uniformly expanding. So I'll assume that the derivative is always bigger than, say, beta, where beta is some number bigger than 1. And if I assume that I have this one-dimensional setting, I have a C2 map, it's expanding, what can go wrong? Very little. There's going to be some natural measure sitting there, which is the absolutely continuous invariant probability measure, which I've denoted by mu. And it should be unique in this particular setting, since I haven't assumed very much. And that's my object. So I start off with my transformation. It's differentiable twice, a continuous second derivative. It's expanding. It's defined on a circle, and it's got a nice invariant probability measure. So what we want to do is to associate to this the number. And the number in this case is the Lyapunov exponent. And so we can associate to the transformation the measure, and then the measure this number, which is the Lyapunov exponent, which will be positive, because I've assumed that the derivative is bigger than, certainly bigger than 1, so it gives me a lower bound of log of beta on this guy, and so that's my number. So I have a number which tells me something about the transformation relative to the natural, absolutely continuous invariant probability measure. So far, so good. The slight difficulty is that in order to define lambda in this way, we have to know what mu is. I know what the transformation is. I'm assuming I've given it. But the question is, what's mu? Well, I don't know. It's given by some complicated implicit identity. So if I wanted to compute it, would I have to figure out what mu is and then estimate lambda? Well, hopefully not, because that's kind of difficult. But in fact, what I want to do, therefore, is find some way to estimate lambda. So the problem is, how can we estimate? Estimate lambda. So regrettably, last year I didn't teach at Warwick. I had to do researchy sort of things or administration-y sort of things. Tragedy that it was. So my writing's a bit erratic now on blackboards. So I need the practice, which I again thank the organizers. Okay, so how are we going to compute this number lambda? We're given the transformation, some specific example. The measure, we know it exists, it's unique, in fact, and it's ergodic. And the Lyapunov exponent is defined in terms of that. So we need to define this value lambda. And of course, the hint is in the title. We're going to use a pressure function. So let me now define it in the easiest way I can think of. So this pressure function, well, in the old days, pressure functions were defined for continuous functions on some space, but nowadays people tend to like just defining it on the real line. We call it P. And this is from R to R in the present context. and it's just defined, by, how is it defined? It's called the pressure function, and it's defined by, in this case, P of t. So t is my point on the real line. And then it's just going to be defined to be equal to the limit as n tends to infinity of 1 over n and the logarithm of the summation over something. And we sum over fixed points for the nth iterate of the map. So t to the n, of course, is just t composed of itself n times. What else could it be? And then for this n-fold composition, we differentiate it and evaluate it at the point. And then I don't need to take absolute values because I've chosen the degree to be positive, but let me do it anyway. And so it's this value to the power minus t. So there's the t. The t makes an appearance. And I chose a circle and a simple example, so I didn't have to worry about limb suits and stuff. So it's just a limit. And so now I've got a function that takes me from the real line to itself. For a given real number, all I do is I take this expression, I look at all the periodic points, which there would be d to the n, I guess, for a particular value of n. And then for each of these, I sum up the derivative around the periodic orbit of a transformation. I get a number, and I raise that to the power minus t. What could be more natural than this, you're thinking? Maybe you're not thinking that, but you could think that. And the good thing about the pressure function is it's got lots of very simple, nice properties, which are the following. So properties of P of t. Perhaps I should draw a line down the middle of the board since I will need probably both halves of it. So how do I define this pressure? I've done it. So now it's got properties, and what are they? Well, the first one is that it's going to have the property that pressure of 1 is equal to 0. Maybe I should draw a picture and exploit the fact that there is colored chalk over here. Oh, very nice. Yellow is always a good color for functions, I find. So pressure of 1 is equal to 0. So it's going to go through this point, if this point happens to be 1. And another property is that it's very smooth. So P is C infinity. In fact, it's even real analytic, but we won't need it particularly. And another property is that, well, two properties are that it's strictly decreasing and that it is, I've written in my notes, concave. So that one is probably positive. So it's decreasing and concave. Yes, I was worried about that. It was going to be concave or convex. Let me say that it has that property. I can put anything one likes. I'm always at the whim of the chairman, so that's fine. Yeah, I think it was a student we used to talk about convex up and convex down. There was something about a smiling face and a frowning face. But I'm just trying to distract you while I think of what I'm going to say next. Okay, I'm going to actually draw this curve. So it's going to look a bit like this. Like that. It actually goes off to infinity, but we don't really care in these two directions. And it probably goes through log of d, but we don't really care about that either. But it looks like that. That's our picture. And the extra bit that we're interested in is the property relating the Lyapunov exponent to this pressure function. So the connection to the Lyapunov exponent, which is just some number, which is kind of nice, is that lambda is equal to the derivative of the pressure at the value 1. So where it goes through 0, it actually has a slope, which maybe will be drawn in a different color. What do we got? There's a kind of pinky one. So And this will require skills I don't really possess, but this is meant to be a tangent vector to this curve. That's meant to be a straight line, almost made it. And so the slope of this, except probably it should be absolute value. Otherwise, it doesn't work, since one is positive and one is negative. So in this case, the slope of this slope is equal to minus lambda. And I suppose I should have written that this yellow curve is actually, so this direction is t, and the curve, of course, is p of t. Okay, so we had our nice map, simplest map I could think of, an expanding map on the circle. We associate to it the Lyapunov exponent, which is something that tells us something about the absolute continuous invariant measure. It's just a number, tells us how exciting it is. And I want to get a handle on that. And the way I've done that is to introduce this pressure function and say that I can read the Lyapunov exponent for this simple case off the graph of this pressure function. Hey, that sounds easy. But was there a question? No, that's good. Oh, so there's a question here. It's written in my notes. Step 2. Question. If we knew P of t, how could we estimate lambda, which is equal to the absolute value of the derivative at 1? So if you had a perfect knowledge of what this curve looked like, how could we work out the value of, how could we extract from this graph the derivative here? And then the answer, of course, is it's kind of easy. So I've written in my notes, calculus 101. We have no such course in England. We don't use such ludicrous titles. I think it's an Americanism. And how does that work? Well, it works in the following way. We fix some value of epsilon, which is small-ish, but not very small, whatever that means. And then the idea is that we look at this picture here, which I will redraw, or at least I would redraw a portion of it. And so this portion I'll draw here. So here is my horizontal line. Then I have my nice pressure function, this yellow curve, which is going to come down here somehow in some curvy kind of way. And then what I'm going to do is draw my tangent. So I've blown up in this picture this region here. Here's, well, again, I have to try to make this tangent look remotely convincing. So this is the line of some particular slope. And so what I do is this point here is equal to 1. This point over here might be 1 plus epsilon. This value over here might be 1 minus epsilon. And then what I can do is look for more colored chalk. It's a festival of color in different shades, perhaps. I don't think I've used blue yet. So, of course, this distance here, from here to here, you might believe, well, this graph, as I just said, was P of t. This was P of t. So this blue distance here is simply going to be the value P1 minus epsilon, because it's positive. And similarly, if I go down here, this distance here is going to be P of 1 plus epsilon, but I have to take the absolute value because it's negative. Right. And so using highly sophisticated calculus, we can deduce that from this picture, we have that lambda, which is this slope here. So it's got slope minus slope equals minus lambda. So lambda is going to be less than or equal to pressure 1 minus epsilon over epsilon. That was the yellow chalk escaping. And it's going to be bigger than the absolute value of P1 plus epsilon over epsilon, i.e. this distance compared to that distance and this distance compared to the distance down to there. So it's just calculus, not even that really. Okay, so if we knew, therefore, the value of P of 1 minus epsilon and the value of P1 plus epsilon and epsilon, then we get upper and lower bounds on this. What could be easier than that? Well, I just leave the problem of actually estimating these things and cleaning the board at the same time. So let me do at least one of these things. So we take our map, we want to work out the Lyapunov exponent for the unique, absolutely continuous invariant probability measure. And we have an expression in terms of the value of the pressure at two different values. I can choose epsilon as I like to make this work. It doesn't make any difference. And then, so we've reduced it to the following question. How can we find well, in this case, we want a upper bound on P of 1 minus epsilon, so upper bound on P of 1 minus epsilon, and presumably a lower bounds on the other one, bounds on the absolute value of P of 1 plus epsilon. Because if we can do that, then we get, of course, bounds here and above, which would still sandwich the value of lambda. Easy, very, very easy. So the question is, how do we actually do that? Well, I defined the pressure using the growth of periodic points with some particular weight, but simply because it was a good way to define it. But of course, the solution to all problems in mathematics, or at least in my kind of mathematics, is to introduce a transfer operator. So we do that. Introduce transfer operator. I think I'm teaching complex analysis at Warwick next year. I'm not sure I can get transfer operators into a third-year course on complex analysis, but I will try. And so this will be an operator, of course, acting on functions. I don't really care too much about what, as long as they're continuous. So continuous functions. Could be analytic, maybe not. Not if the transformation is only C2, but if it's C2, at least it can act on continuous functions. And so the definition of that, which we've seen variants of before, but since I'm looking at a particular setting for this pressure function, it's going to be defined as follows. So I choose a value of T, which is in R, the value for which I want to say what the pressure function is. And then it says that L of T, so there should be operators, because there's going to be lots of them. And it's going to map me from continuous functions on my space, which is only the unit circle, to itself. Somehow my S's are looking more like rows, but that's meant to be the unit circle. And the operator itself is defined in the time-honored way. We take some function, which is in C0 of S1, and then the operator applied to that, evaluated at some point. So the X is going to be another point on the circle. It's just going to be that we sum over the pre-images of the map, which is degree D, so it'll have D pre-images. So it's a set of Y such that T of Y is equal to X. And then, of course, what we do is, not what I've written in my notes, 1 over the derivative at the point Y, all raised to the power T, I guess, times F of Y. So that's my definition of the operator. It's just mapping continuous functions to themselves. And the way it does is it averages over the pre-images of every point with a weighting, which is just given by the reciprocal of a derivative, raised to the power T, since we want T to also feature in here. Okay, so now we have that we want to estimate the Lyapunov exponent. We know the Lyapunov exponent is given by the slope. Using higher calculus, we've deduced that the slope is actually written in terms of two values of the pressure function. And what we don't like is this definition of the pressure function. It involves too much effort to compute it or estimate it. So we're going to use the transfer operator instead, which works perfectly well if we know how to write it in terms of a transfer operator. But indeed, the hint is given over here, where it says possibly it's the maximal eigenvalue for this guy. And so, in fact, in this case, the pressure function will be given in a simple way. Not perhaps quite the way you're thinking I'm going to write it, but something a bit like that. So my alternative definition of the pressure is going to be the following. So this is an alternative definition of the pressure function. And the alternative definition is the following. Well, here's P of t again. For simplicity, I'll raise it to the power e. And so my alternative definition is this is going to be the limit as n tends to infinity. I'm going to take a function f, which I haven't said what it is yet. I'm going to apply the operator n times. I'm going to take the subnorm, because these guys are all inside continuous functions on the circle. And then I'm going to take the nth root. And that's an n. Looks like an h, 1 over n. And the claim is that this is going to be this. So what's my function f? Well, here, f is going to be any continuous, so for any, f is a continuous function in on the unit circle, but I'll also assume that it's strictly positive. So for any strictly positive function on the unit circle, I apply the operator for a given value of t, lots and lots and lots of times, n being the number of times. It goes somewhere, we take the subnorm, take the nth root, and that's my new definition of pressure. And it's the same. Why is it the same? Well, it's due to the Royal operator theorem, but let's give the old guys a plug. We'll all be old we'll all be old sometime ourselves. Okay, how does this help us? So we know that we want to get an estimate for the value of the pressure at 2 different values to give us bounds on this derivative. And now I've written down that I can write the pressure in terms of this transfer operator. Well, there's 2 claims. Here is one of them. So, and this is going to be the upper bound on the left-hand side. So this is going to be the upper bound on the pressure of 1 minus epsilon. And it says the following: if I can find a value beta, so it's a real number, which is positive, and I'm trying to get the grammar right, which is always a bit difficult when you're writing, and a function which I'll call f minus. So f minus is going to be a continuous function on the unit circle, which is strictly positive. Let's assume I have such an object. And it's going to have the following property, which I think I'm going to put down here. So such that something is true. And the something is that if I take my function f minus and I multiply it as a whim by the exponential of beta, this beta, and that's what I get. I've just scaled it up. And if it has the property that this guy is always greater than or equal to the operator where I take the value t to be 1 minus epsilon of f minus, let's say this is true, and this is true for every point. So this is true for all x in the circle. Then what does it tell me? Then it tells me that I get an upper bound that the pressure 1 minus epsilon is less than or equal to beta. So it's a way to fish around to get an upper bound on this beta. So the picture I sort of have in mind is that if you think of the unit circle as looking like a straight line, because I can't draw circles that well, then I have a function f minus. I'm scaling it so it becomes, possibly it should be defined over the domain. So this is meant to be e to the beta f minus, which is this guy. And then I apply the transfer operator to f of minus. So there'll be another function around, which is down here. And this will be L 1 minus epsilon f minus. And I'm asking that for every point, one function is bigger than the other. And that's enough to guarantee that the pressure of 1 minus epsilon is less than beta. And the proof of this is extremely trivial. So let me inflict it on you. I was going to say it takes 2 lines, but my handwriting is kind of big on the notepad, so it probably takes more like 5 lines. But you will see the simplicity for yourself. So that's my first claim, claim 1. So proof of claim 1. Okay, so the observation here is that since e to the minus beta L1 minus epsilon as an operator is positive, so it acts on continuous functions and it maps positive continuous functions map to themselves. As it usually does, then in fact, I know that the function f minus at some point x is going to be greater than or equal to e to the minus beta L 1 minus epsilon applied to f minus. Why do I know that? Because I'm assuming it in the statement, this guy. I'm just taking the e to the beta over to the other side. So nothing has happened. So this is true, but then I can apply the operator, I can apply the same object to both sides of this equation. And so the left-hand side becomes the right-hand side becomes something smaller. And then if you keep iterating it, you get this goes down to something like e to the minus n beta times the operator L to the n 1 minus epsilon, iterated n times. Trying to apply to f minus. So this is just by positivity and this identity at the top. And so in particular, if I think about the size of these two things, we get that the left-hand side, when I take some limit, looks like e to the minus beta. I'm going to take the nth root of it after I've taken a supremum. So this gives me that 1 minus beta n tends to infinity. Let's say the subnorm applied 1 minus epsilon times to f, infinity 1 over n. Well, this thing is supposed to be smaller than the stuff over here, but if I take the nth root of that, it's not very exciting. It's going to be less than or equal to the limit as n tends to infinity, some subnorm of f minus, these are f minuses, the infinity to the 1 over n, but this isn't changing with n, so it's just equal to 1. And this object here, I've asserted is the same as the pressure. It works for any function, including f minus, so this is going to be e to the pressure 1 minus epsilon. So it gives us e to the minus beta times e to the pressure 1 minus epsilon is less than or equal to 1. And so using even more advanced calculus, we can deduce that we have the right inequality, we hope. Usually I have to do this calculation lots of times because I get it wrong enough times that it could happen again. And that's it. That was easy. Nothing much happened. So that gives us a bound. It gives us an upper bound on the pressure of 1 minus epsilon. And of course, there's a similar argument with a similarly simple proof, which works in the opposite direction to give us a lower bound. And let me just state it briefly without inflicting the proof on you. So this is claim 2. What does this one say? So this is a lower bound on the pressure of whatever else I'm looking for. Maybe it's 1 plus epsilon. I should take an absolute value. Okay, and it's a similar statement. So given some value alpha, say, which is going to be positive, if there exists some function f plus, which is positive and continuous, with the property of L of 1 plus epsilon applied to f plus is less than or equal to e to the minus alpha times f plus. Let's say we can find a function and a value of alpha with this property, then it's going to give us the lower bound. So the absolute value of pressure 1 plus epsilon is going to be greater than or equal to alpha. Okay, so we were interested originally in a simple dynamical system, an expanding map. We associated to it this Lyapunov exponent, which we didn't know how to estimate offhand. And I've introduced the pressure function, and then I've introduced this operator. And the question is, where have we got to in all this? Well, the point here is that we now have a bound, very simple. So the conclusion here would be, conclusion, if we can find alpha and beta numbers and functions f minus and f plus with the above properties, so for such f plus, f minus, it's a comma, alpha and beta, we would get that lambda, the number we might want to estimate, lies between, would you believe, beta over epsilon and bigger than alpha over epsilon. So it gives us some way to do it if we could find functions f plus and f minus, and we had some intelligent idea about what the alpha and the beta might be. And if this argument here, this simple argument here looks vaguely familiar, I should say that if we could somehow replace f plus and f minus by locally constant functions, it's a bit difficult to do for continuous functions unless they're completely constant. But if you had a Markov partition, you could do it. So if we were, then this argument would be very similar to the argument we've seen before, which was the Collatz-Wieland, which I can't spell, Wieland theorem for matrices, which of course appeared in the talk of Warwick Tucker. So all we've basically done is kind of upgraded from matrices and constant functions to operators acting on continuous functions by some sleight of hand. So if we are given a dynamical system T and we wanted to write down these f pluses and f minuses, some smart choice and some smart choice of alpha and beta, how do we do it? Well, what we can do is use time-honored methods to estimate these things, and then somehow this gives us a way to make it more rigorous. That's basically what's happening here. So in practice, we would choose f plus and f minus chosen using something. So we use some approximation method. Maybe for the transfer operator or something like that. So e.g., maybe Lagrange and Chebyshev. There's a slight pause here because I'm trying to remember if Lagrange was involved in the annexation of Tuscany by France. Was that sound vaguely? Let me just make that up. It sounds good. Alpha and beta, where do these come from? Well, we just choose any one we like, and we get better estimates using a bisection method. We just keep improving our choices. And how do we choose epsilon? Well, we want a value of epsilon which is relatively small so that we can get the alpha and beta close, but we don't want it so small that it's going to blow up the denominator. So this is chosen by trial and error. Sort of Goldilocks thing, not too small, not too big, just right. And so this Lagrange Chebyshev idea has appeared in Julia's talk. And the bisection method was also mentioned in Warwick Tucker's talk. Warwick's talk. And so that's basically how we do it. So as we say in English, the proof of the pudding is in the eating. So does it actually work for anything? Well, the answer is sometimes. So on the back of this board, I've written down an example, which is almost in this class. So here is an example which is close to being a doubling map. So you take x goes to 2x mod 1, plus you perturb it by something. The astute amongst you will notice that it's not actually C, probably not even C2, but it works anyway, the method. And so what we want to do is to look at the absolutely continuous invariant measure for this expanding map on the interval of a circle, and then compute its the Lyapunov exponent for the absolutely continuous invariant probability. I don't know what the absolutely continuous invariant probability is. It's some measure. It's got some complicated density, which I prefer to stay away from because it's complicated to deal with. So therefore, I can try to do all this stuff, and I can make choices of f plus and f minus. They're meant to be continuous functions on the interval. Well, in fact, I look at polynomials of up to degree 300. It's a good number. And then it gives you an estimate on the Lyapunov exponent, which is accurate to 165 decimal places. That's the theory anyway. So as a method, it's quite effective if you want to estimate Lyapunov exponents. And in the subject matter of the talk, I'm talking about Lyapunov exponents. I could be talking about Hausdorff dimension, maybe. It's the same method because you want to express the Hausdorff dimension in terms of the pressure, and you say stuff like the Bowen-Ruel identity, blah, 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 blah. And then there's a way to get your hands on the dimension of certain sets, if they're nice sets, using this approach. Or if you were interested in central limit theorems and you wanted to work out the variance in the central limit theorem, again, you can also get your hands on that because it's related to the second derivative of the pressure at some value. So all I'm doing at each stage is saying that numbers I might be interested in, I can extract, this is an extraction gesture, I can extract from the pressure function, and I get my hands on the pressure function because I think of it in terms of a transfer operator in this way. And then it just comes down to a rather trivial estimate up here. So if I was doing some Ulam-ish type things, then I'd probably be looking at matrices, but then the matrices were giving me too much information. It would be approximating all of the spectra. I'm only interested in the top eigenvalue. And it would also probably be harder work because if I retain some smoothness here, I can look at polynomials and it goes faster. Let me just mumble those lines. So in the remaining 8 minutes? Sure. 8 minutes, let me just give you a hint about matrices. So this is the second application. So I've defined the Lyapunov exponents in the context of expanding maps, but there is another context in which they are quite popular. And that's in the case of random matrix products. So let me just say a bit about that, not too much. So to give the impression that there's a whole variety of things you can do, rather than just a small number of things. So this is to do with matrices. So we've moved on from maps to matrices. What sort of matrices will we like? Well, for simplicity, I'll take the simplest case, which is I'll assume I've got two matrices. Could be D, but it's going to be 2. And I'll also assume that they're 2 by 2. So, and real valued. So let's assume all these things. And then the idea is that I want to randomly multiply these guys together. I'm also assuming, therefore, they've got determinants equal to 1, which is not much of a restriction. And then in this case, there's also a definition of a Lyapunov exponent, but it's slightly different. And so in this case, the Lyapunov exponent, well, it's given by some formula. Well, it's also denoted by something. Let me call it lambda. And of course, it depends on my matrices A1 and A2. And I rubbed off the previous definition of pressure, but I'm sure we all remember it. And in this time around, it's given by the following formula. So lambda is equal to the limit as n tends to infinity, 1 over n of the summation. It's maybe 1 over 2 to the n would be a bit better there. of some summation. I'm summing over I1 up to IN. What are these guys? They're just indices, 1 or 2. So here I'm going to have 2 to the n choices. And what do I do with my choices? Well, I multiply the matrices together. That's AI1, meant to be matrix multiplication, AI2 down to the end, AIN. I take some norm of them, and then I'm trying to remember what I do then. So this is just a matrix product. And the idea is that this limit will exist by some subadditivity stuff, and it's equal to lambda. And this is just a matrix norm, but I can take any one I like. It all comes out in the limit, or the wash, matrix norm. So give me 2 matrices, and then I can associate the Lyapunov exponent, which is a kind of average growth rate of the norms of these products of guys. That's morally what it is. Yes? Sorry? Should there be a logarithm? There should indeed be a log, and an n, in fact. Thank you for that. There should be a logarithm here, and I should also divide out by n. My enthusiasm for what came next distracted me from completing the equation. Anyway, so in this context, let me content myself for the moment with the simplest possible case. And the simplest possible case would be if the matrices all have positive entries. If they don't have positive entries, you can still do stuff, but it's certainly easier in the case that the entries are positive. So let me just write that down. Easy case. We all like to live on the easy street. Easy case. All the entries in each of the matrices, so it's only 8 in total, are strictly positive, not even allowing zeros. So we just do the same sort of thing as before. We do the following. So I'll denote by delta. It's going to be the simplex. So that's going to be all the points x, 1 minus x in the plane, where I'm allowing that 0 is less than x is less than or equal to 1. And that's a set. So this is the simplex. And here's my quadrant. And my simplex is going to be apparently pink. Here he goes. There you go. That's my simplex delta. And it goes from 1 to 1, and here's 0. And what do I do then? I look at the maps Ti, which are going to map me from delta to delta. And these are going to be the maps I equals, where I is 1 or 2. There's 2 maps for the 2 matrices. And these are just the projectivizations. So Ti of psi is just we apply the matrix presumably on one side or the other, maybe on the right. And then we take the norm of that. So that's matrix multiplication. We get another vector. So the picture should be something like the following. Here's 0. This region is the positive quadrant. And the matrices are positive, so they map the positive quadrant inside itself. So this might be the image of the quadrant under AI, matrix multiplication. But if I had a point which I call psi on my simplex, and I apply the transformation, then first of all, it gets mapped further away as a vector, but I'm scaling it back. So it would be Ti of psi. And we do this for each of the matrices, and they look like whatever they look like. And that gives me the transformations. Okay, and then as before, we want to introduce transfer operators because that helps us out a bit. And so what we do is we introduce transfer operators. So in the case of the expanding map of the circle, we looked at continuous functions on the circle. And here, of course, we look at the continuous function somewhere, and it's going to be on this simplex. So we introduce these transfer operators. They're in the plural. So for every t, we define LT from continuous functions on the simplex to itself in a way you can possibly guess. So t is a real number. And the way it's defined is L(t) of a function, which I've called f again, lacking imagination. So f is going to be a continuous function on the simplex, and psi is going to be an element of the simplex itself. So the image function at the value psi is going to be, again, an average. It's a half of the summation I equals 1 up to 2, i.e. there's 2 terms. And it's taking f of ti of psi. So it's taking this point psi to this point, evaluating the function there, but then it's multiplying it by the derivative of the map at the value psi. And we need to squeeze the t in, so the t goes at the end like that. So these things are like contractions, which is why it's going to be t and not minus t. Last time around, it was expanding maps. Anyway, this is an honest-to-God operator, one hopes. And so in particular, it allows us to define some properties. In particular, we can define the pressure in this context. And the pressure looks pretty much like it did before. So it says in my notes, so definition. We introduce this pressure function, so we let P from, well, it's going to be real line to itself. That's good. And this is going to be defined by, be defined by, no comma, be defined by, how is it defined? It's defined by saying that e to the P of t is going to be equal to the limit as n tends to infinity, of the norm of L to the n t applied to some function f. I'm taking the subnorm, I'll take the nth root, and I can take any function f, which is continuous on the simplex, and it's also convenient to assume it's positive, otherwise it's not true. So now I'm interested in this number, Lyapunov exponent here. I want to express it in terms of the pressure, and then by analogy, well, in fact, we can say the following, that this map is a nice map. It looks like this. I'm keeping my eye on the time. And the curve, well, now it's going to go through 0 for some change. Here is 0. This is P of t. It's going to have a certain slope at that value. I should have said that. I said so it was P of t. And so, in fact, in this case, the absolute value of the derivative of this nice smooth map at 0 is going to be the value of lambda we're interested in. So, as before, we can introduce lots of guys like alpha, beta, f plus, f minus by playing around with them to get estimates on lambda. So the slope here is slope equals minus lambda. So it's almost exactly the same picture as before. The pressure function has very similar properties because it's really just the same sort of thing. And consequently, you can do the same story. So you can work out in this positive case, the Lyapunov exponents quite easily, numerically. If you're not in the positive case, then you have to make more assumptions to make it work. Kind of helps if your operator still has a positive eigenvalue. So maybe you need something like, you know, strong irreducibility, proximality, lots of words like that. And you have to choose this value of epsilon, which I haven't introduced here, but we choose epsilon to define epsilon greater than 0. So we take t to be equal to plus or minus epsilon, as we did before, but we have to choose the epsilon quite small because we don't know that the pressure function extends to everything. So beyond this setting, life is slightly more complicated, but the principle in each of these cases is exactly the same. We're doing exactly the same argument, nothing fancy. It's just a version of old ideas revamped and used in this particular setting. But it seems to be quite effective in some cases. And so you can, as a final comment, which I won't write on the board, by way of applications, one could work out the Lyapunov exponents for these matrices. Well, the matrices might correspond to generators for a Fuchsian group acting in hyperbolic space, in which case the Lyapunov exponent has an interpretation. It's the drift. It's how far fast things move out. And you can use these to get estimates on the Hausdorff dimension of the hitting measure at infinity of random walks in hyperbolic space. That's my random walk gesture. And also, if you could upgrade this a bit to higher dimensional matrices, 3 by 3, then one could attempt to get estimates for their Lyapunov exponents. And they have applications to things like computing Hausdorff dimension of things like the Rosy gasket. Another great French mathematician to throw in there. And that was it. Let me just stop there. Thank you very much.
Okay, initially I was a bit like, maybe I should ask about this giant number.
I'm wondering why Caroline doesn't get a microphone. I think this answer is now being answered. It's okay.
Thanks. So I'm wondering, so maybe my first question is, what precision did you use to compute that? Did you use 110 to the minus 145, or did you use something a lot bigger?
No, I used Polina to calculate it.
Okay, cool. All right. So Polina, no, okay. So I guess like, I'm kind of curious about this computing Lyapunov exponent by taking a like kind of a numerical derivative. It's more or less what it is, right?
Mm-hmm.
Because usually when you take a numerical derivative, you introduce a lot of kind of error, right? Because you divide by something very small with epsilon. So you need to know the estimate of your eigenvalue to a much bigger precision, a much better precision than you expect.
Yes. So if you wanted to get it within epsilon, then you have to choose the precision and the pressure to be like epsilon squared or something like that.
Yes.
So yes, the answer to that is yes. That's why I said that when you introduce epsilon, you choose it small, but not too small.
Yeah. Okay. So you kind of lose. Is there a way that you could kind of do better? Yeah.
Me personally, no. Other people, maybe.
Yeah. Thanks a lot. I think I got distracted, so I didn't understand how you find these F plus and these F minus, because I mean, I understand you find them in polynomial of some degree, but probably you have to optimize something, right? You cannot, so what do you do exactly?
Right.
Sorry, since I'm at it, and another question is, what about if I don't want just the maximal eigenvalue, but the other one? Is there any way?
Sure. There's always a way. Yes, I was a bit distracted in the middle of a talk as well, but let me try and remember what happens. Yeah, so the point is that we want to estimate this derivative by getting the values of the pressure at these two guys. It's going to be some maximal eigenvalue for some matrix. Well, what we want to do is to use some method to estimate the top eigenvalue for these transfer operators for pressure for t equal to plus or minus 1. And the way we do that is just to use an interpolation method. So all we're doing here is approximating the operator by something. I mean, this is the sort of numerical analysis approach. And then once we find a function which we can use, which corresponds to an approximation to the eigenfunction for the operator. So we have a value plus 1 minus epsilon, 1 plus epsilon. So that's two numerical values. We have the operators. They have eigenfunctions, which are honest to God functions on the space. We don't know what they are, but we can approximate these eigenfunctions by approximating the operator. That's the interpolation bit. Yeah, it would look like Ulam if we're looking at locally constant functions, but in this case, we're not. We're approximating. In this case, you may have noticed that my examples are actually fairly smooth. Okay. So in fact, the analyticity there helps you because you can preserve analytic functions and they're being approximated by polynomials. If we go up to, if we look at settings where it was just C2, then of course life would be worse. We could only approximate by lower degree polynomials and stuff like that. And that would be worse. So so the analyticity works for you in this case as well. And the answer to the other question was, yeah, the positivity isn't if you want the other eigenvalues, so other Lyapunov exponents, well, in the case of 2 by 2 matrices, it's not so hard. But in the case of higher rank matrices, like 3 by 3 or something, then you can take the matrices and you can take wedge products of things. And that will give you another bunch of matrices whose top Lyapunov exponent, which is always the thing we're working out with top, would be the sum of the first two Lyapunov exponents of the first guy. You lose positivity. So so you need that the matrices that you have that are not positive, you can still deal with. And we can deal with them to some extent, but not as well. And the reason it's not as well is because we have to look at continuous functions on maybe projective space, on the sphere, maybe, rather than on this guy. And we don't get contraction, but we get some sort of contraction on average, which all comes from the work of the Rennes school of extremely good mathematicians like Lepage, Guivache, Raji. How do you say Raji? Raji, merci bien. And other great people there I've forgotten about. Maybe Cons as well. Where'd the chocolate go?
So, in a sense, this method is much more naive than method based on zeta functions.
My speciality, naivety.
Could you compare the accuracy compared to I don't know, the computing power you require? Or?
Yeah, I mean, so this method is essentially what you might call a suck it and see method. So what's happening here is that we get an estimate on the error, but of course a priori we don't really know what these values alpha and beta are. We just keep plugging on until it doesn't work. It churns out these functions f plus and f minus, and it gives us an answer, which in this case works like this. So in the examples that you study, that we have studied, it's quite efficient. But we look at settings, for example, where there's a lot of hyperbolicity and stuff like that. That makes life much easier. So the zeta function thing is quite good in some settings. So if you're reasonably hyperbolic, it converges very fast. So maybe it would give you let's say it gives you the first 10 places very quickly, but then it slows down. And the reason for that is because you have to work out all the periodic points. It's closer to the original definition of pressure, where you count all the periodic points, and you have to keep track of all these guys. And so if you look at periodic points of period up to 25, there's an awful lot of them, 2 to 25, for example. And so it slows down because although it gets more and more efficient, you're doing much more work as you go along. Whereas this method, if it's only dealing with polynomials of degree, it's a different question. But here you're dealing with polynomials of degree 300. I mean, the computers are happy with that. So it's naive, but it works in some cases, and it works to give you the top number. The zeta function approach is quite good in the short term, medium term, and it also gives you more information like the resonances, which this doesn't give you, and stuff like that. Well, they give you the eigenfunctions at 2 different places. So if you wanted to know the invariant measure, it depends how you want to know it. I mean, if you wanted to give me a test function and you wanted to know what the integral of that test function was with respect to this measure, providing your function was kind of reasonably nice, then I think you could do it. But otherwise, I don't know how to present the measure in a way which would work in the scheme. I should also mention that I presented this as a kind of very general, easy, naive method. I should also mention that for example, the example over there comes from a paper with Polino sitting in the second row, and also I've been collaborating with Julia on this as well. I should give the girls a plug, so to speak.
Thank you. So I'd like to thank the organizers for inviting me to this conference and for the invitation to give this talk. Whether this last idea was a good one, you will decide. Okay, so yeah, so my goal is to present some old and new results about, let's say, the entropy theory of these dynamical systems. So these results are not really for directly connected to things that have been clearly visualized or computed, but I'd like to take this opportunity to point out where we have things that go into that direction, that suggest that some things, at least in some cases, should be computable, and that seeing them more concretely might also advance our understanding. Okay, so this is the plan. I will start by reminding you of some basic stuff. First in the topological setting, then for a smooth surface diffeomorphism. Then I will talk about some new results with Sylvain Crovisier and Omri Sarig that really give us some objects that we would like to understand. Okay, we'll see at this point probably that, okay, it doesn't look very easy. Let's say it looks challenging. And so before concluding, I will show you something else that might be related or maybe not, but for which I have a picture. Okay, so very quickly, okay, what is how you can define the topological entropy? So I don't want to, the formula are there, so I don't want to really to go into details, but you see that, so for instance, topological entropy is when you compute the number of orbits in some sense at some scale, and then you let the scale go to 0. Okay, so topological entropy, you count everybody. So the Kolmogorov-Sinai entropy, that is the entropy of an invariant probability measure. Okay, in the ergodic case, you have a similar formula due to Katok. Okay, where instead of considering all orbit segments, you consider in some sense those that are relevant for your measure. And you have the same structure. You compute at some scale epsilon, and then you let this scale go to 0. And finally, maybe less well-known, but important quantity is what is called now the tail entropy, and was introduced by Mizoevich under the name of conditional topological entropy, which is this H star. Okay, so the formula gets even more exciting. What it means is that you, at the scale epsilon, you ask yourself, okay, what complexity, what entropy can remain? Okay, you look everywhere and you say, okay, if I know up to epsilon what I'm doing, what surprises could I have on a much smaller scale delta? Okay, this is the tail entropy. If you think a little bit, if I gave you the time to read these formulas, you would say, okay, this is a uniform bound. This H star at scale epsilon is a uniform bound on what my distance to the limit when epsilon goes to 0. Okay, so yeah, I forgot to say, it's written there. So all this works for a continuous map on a compact metric space. Okay, and so these are definitions. And one of the key results is the variational principle that dates back to the early 70s that tells you that in this setting, the entropies of measures approximate the topological entropy. So you see, so up to some technical stuff, which is made obvious by this choice of definitions, you see that for any measure, the entropy is less than the topological entropy. What this variational principle tells you is that actually you can find measures with entropy arbitrarily close to the topological entropy, which is therefore the supremum of these entropies. So I'm not going to go into the proof. I mean, there is a very nice proof due to Mizoevich, which, and the idea is important. It goes like this. So, okay, I'm cheating, but I can. So you are thinking about this formula. So you fix some small scale epsilon, okay, and now you have this growth rate, okay, and this is the growth rate of what? The number of orbits of length n that you can distinguish at scale epsilon, okay, and this is what it means. This set is just okay, and to build a measure, what you can do is what Isoevich did was essentially you take such a set corresponding to discounting. You just put masses at each point. You push a little bit so that in the limit it will become invariant. Okay, and then there is some technical computation, clever but not very hard, that tells you that the limit when any accumulation points when n goes to infinity will have entropy actually like the growth rate of the cardinalities of these sets. Okay, it's a very standard, but it's an important way to do. Okay, so what you, and since and by definition, you take epsilon arbitrarily small and you get measures, let's call them mu epsilon, which are arbitrarily close in entropy to the topological entropy. Okay, and this is the rational principle. You don't know that you can let epsilon go to 0. Okay, so I should say MME means measure maximizing the entropy. It's just that it's long, so okay. So can you take the limit? Can you get a measure more generally with exactly the full entropy? Okay, so for now we leave topological dynamics. We go into smooth dynamics, and there is this theorem by Newhouse that tells you that in fact, if you are if you have C infinity regularity, then yes, you have a measure that achieves this supremum. Okay, and what is the proof? The proof is to deduce from Yamdin theory that the tail entropy is 0 when F is C infinity smooth. Okay, and then notice that this property gives you uniform convergence, uniform with respect to the choice of the measures of the measure in the Katok formula for Kolmogorov-Sinai entropy, and this gives you upper semi-continuity. I mean, this is something that was already remarked by Mizuevich, and actually this is why he introduced this notion. Okay, and now the new thing that Newhouse, okay, so I thought there is a typo, that Newhouse proved was that Yamdin theory, which is about local complexity of, let's say, a smooth map, gives you this annulation. Okay, now something I want to point out is that so David Burguet, Gong Liao, and Yagong Yang proved actually obtained estimates on the rate of convergence. Okay, and they have upper bounds. They have also some lower bounds in terms of the growth of the let's say the supremum of the derivative of higher and higher order. Okay, so this, so and the answer, well, in general, it can be bad. In good cases, it is like a little bit worse than 1 over log of epsilon. Okay, so this tells you that, okay, so you can compute entropy. You can have an upper bound on topological entropy, for instance. Computing at a fixed scale, epsilon, but this scale has to be very, very small with respect to the error that you are willing to tolerate, because, okay, it only goes to 0 like 1 over log of epsilon or worse. 1 over log of epsilon, I'm simplifying a little bit, is for the best case, like analytic on a surface. Okay, otherwise it can be much worse, but there are estimates. This annulation of the tail entropy, it goes even beyond C infinity. I mean, there are a lot of stuff I don't want to. But if you're not C infinity, if you are just CR, then essentially, unless you have a very good reason to have that it is 0, like this previous situation, in many cases, I don't want to say it precisely, it is actually a positive. But when it is 0, actually the estimates that underlie this have some uniformity in the diffeomorphism, and you get that the entropy as a function of the diffeomorphism is upper semi-continuous. Okay, so you have two upper semi-continuity, or it is in fact jointly upper semi-continuous as a function. So the topological entropy is, and this was the Kolmogorov-Sinai entropy. Okay, here you need a little bit more than that, but actually the proof of that gives you what you need. Okay, so when you have this tells you, and actually it's something that the knowing this, in fact, tells you that, okay, if you have astronomical amount of computational power, then you can prove better and better upper bound on topological entropy. You can say something like it is semi-computable. So you can imagine easily, knowing this theory, an algorithm that will produce better and better upper estimate that converge to the topological entropy, but in general, it doesn't give you, you don't have the lower bound. So it's only semi-computable. You don't know where to stop, when to stop. Okay, so now let's go to surfaces. So for surfaces, okay, you in fact have the lower bound. Okay, it was in fact proved before by Katok, who proved that the topological entropy of a C2 surface diffeomorphism is in fact, you can read it as the supremum of the topological entropy of uniformly hyperbolic subsets. Okay, so these are some type of, you can consider horseshoes. So these are robust invariant sets, okay, that you can in principle detect with the same remark about the amount of power or time that you would need. And this time, these give you lower bound. Also, they are robust with respect to C1 perturbation. So this gives you the lower semi-continuity you had by, so dimension 2 gives you lower semi-continuity. C infinity gives you upper semi-continuity. So in this setting, you get continuity of the entropy. And okay, if you don't care about how long it will take, you could compute the topological entropy of a surface diffeomorphism. I don't know if there is any reasonable way to actually do it. I mean, certainly it is computable, but whether it is something that can actually gives you an answer, a reasonable answer is this. I have no idea. I mean, since we saw that the tail entropy converged to 0 very slowly, probably the answer is negative. I mean, not if we cannot efficiently. Okay, so now, yeah, so we know by Newhouse result on the previous slide that there are measures which realize the topological entropy, so which have the full complexity of the system. Now you can ask yourself, okay, how can I see them? Okay, since this is about computation and visualization. So there are some results that point to a possible way. So one such result is a result of equidistribution, okay, which is a combination of a number of results. But the key step is by David Burguet quite recently. It essentially tells you that as in the uniformly hyperbolic case, periodic orbit will equidistribute according to the MME, the measure maximizing the entropy. So either you think of it as if I can compute this measure in some way, it will describe to me how the periodic points are, or maybe this is a way to visualize the MMEs, okay, by computing a lot of periodic orbits. So I should say that you cannot, I mean, in general, it doesn't work if you count all periodic orbits. What you have to do is consider only hyperbolic periodic orbit. And actually, this is not enough. What you have to do is to consider periodic orbit whose Lyapunov exponents are uniformly bounded away from 0. Okay, so it's known by the results of Katok that if you take a lower bound which is strictly less than the topological entropy, then you will have many periodic points, many hyperbolic points with this lower bound chi. Okay, I will say chi hyperbolic points. Okay, so first as numbers, essentially you have a logarithmic estimate that tells you that the number of such periodic points is exponential the period times the topological entropy. Okay, there is a possible period that appears, which makes the correct statement a little bit more complicated. And then when you take with the same, not only they have the right number, but actually if you do like Misurevich, then what you obtain in the limit is any accumulation point will be a measure maximizing the entropy. Okay, so it gives you, it's the first way to access these. Chi has to be reasonable. So chi must be positive. And then you should have periodic points. Okay, so what is known by a lower bound proved by Katok, improved by Sarig, is that if you take chi strictly smaller than the topological entropy, then it is okay. David Burguet's theorem is more precise. It tells you, okay, if you have some positive chi such that the lim sup is the topological entropy, then you take the same subsequence, you do this construction, any accumulation point is an MME. Okay, so here really the lower bound, in fact, it proves a kind of separation property between periodic orbits using the C infinity assumption, and the surface assumption. It's a quite difficult theorem. Okay, in particular, if you remove the lower bound, okay, you can say, okay, let me count all the periodic orbits, all the hyperbolic, periodic orbits, so that I have a finite number for each period. Then it's known, okay, Kaloshin constructed example already a long time ago that tells you that you have lots of diffeomorphism, even surface diffeomorphism, even smooth one, for which this is infinite. I mean, if you remove chi or you put chi equal to 0, this is this can be infinite. In fact, you have open set, non-empty open set, where you have a generic subset where if you count all periodic orbits, all hyperbolic periodic orbits, it just blows up arbitrarily fast. Okay, so really you need some to put something. Katok results told you that you had the lower bound, not with a period, but okay, almost the same lower bound. And here the big news is the upper bound if you put this chi. So, okay, so then let me say I'm just the theory guy, so I ask you, okay, very well, these guys, Burguet, Katok, Sarig, have worked hard. Okay, can you do something with it? Well, I certainly cannot, but okay, so as we heard in the questions to Mark Pollicott, of course, it's really painful to have to compute periodic orbits. I mean, since, as we say here, there are exponentially many of them. So it's not at all clear that this is really reasonable, but it's a question. And we'll see a little bit later that actually one could hope that maybe by modifying the set of periodic points that we want to count, there might be on the theoretical level, let me say, rate of convergence. Okay, telling you, okay, if you go up, that something will decay exponentially in n if you consider orbit of period n. Okay, so so we had this result of Burguet, and now still in this in the same setting. Okay, so the MME. So in Burguet's result, we just obtained that any accumulation point of the high hyperbolic periodic orbits is a measure maximizing the entropy. Okay. Here we have a finiteness result that tells us that, okay, in this setting, in fact, we have finitely many ergodic MMEs. So I didn't say, but okay, the entropy of a measure is the average of the entropies of its ergodic component. So for MMEs, it's essentially equivalent to consider ergodic ones. Okay, so here I could say there is a finite dimensional simplex of measures maximizing the entropy. It's completely equivalent. This one is simpler, at least for me. So I say it like this. So as I said, there are finitely many of them, and we have some information about them. Not a lot, but still. So one good thing is that you have semi-continuity with respect to the diffeomorphism. Okay, this means, for instance, that the number of ergodic MME is upper semi-continuous. When you perturb the map, it can only drop. Okay, and the proof and some structure that will come later, okay, gives us some handle, but not a lot of thing. Okay, if the map is topologically transitive, if there is a dense orbit, then it's even better. The MME is unique. Okay, so then we can really say it's going to be continuous as a function of the map and things like that. Okay, so we have this theorem. It's proved using a lot of stuff, including symbolic dynamics. So we use a previous result that I mentioned on the slide before of Sarig about Markov partition. But the Markov partition, well, already in the hyperbolic, uniformly hyperbolic situation, Markov partition are not so simple object. Here, okay, it's a little bit frightening, at least for me. So first thing, it is countable. So the rectangles are neither closed nor open. And the whole construction, which is extremely general, it applies, I mean, Sarig's construction applies to any surface diffeomorphism, let's say C2 surface diffeomorphism, and is able to represent all measures, all invariant probability measures without zero exponents. And there is a generalization by Sneer Ben-Ovadia to any dimension. So it's very powerful, but the price you pay is that it is very abstract. Okay, so in particular, one thing that you could think of if you wanted to approximate a measure maximizing the entropy for an OSOF map would be to use the symbolic dynamics, to use the Markov partition. Okay, and to say, okay, you can try to compute it or to get some approximation of it, and then you will be reduced, or at least you will be able to use this structure. Here, I have really no idea how to approximate in any sense that I could think of the Sarig Markov partition. Okay, so that's bad news, certainly. Okay, so the piece of good news or non-negative news is this topological structure. So that we, in the course of this theorem, we are able to study the support of these measures. So each time you have an ergodic MME, in fact, you can describe its support by, there is a hyperbolic periodic orbit which is related to it. And how do you find the support of mu? So you take some relevant periodic orbit, you consider its stable set, because this is the set of points that converge. Okay, it will be automatically exponential in the future. This is the stable set, sorry. You have the unstable set when you iterate negatively. Okay, this by very classical result, these are immersed submanifolds. Okay, and now you can consider whether they have intersection points. You take the transverse intersection points. Okay, you get a bunch of points. Well, there are some, either you will have finitely many, then this means that the intersection points are just the periodic orbit itself. Okay, if you have a measure in this setting, it will not be finite. Once it is not finite, once it is not reduced to the periodic orbit, you get uncountably many things. You take the closure. this gives you a compact invariant set which is topologically transitive and which contains a lot of horseshoes. So this is which is called classically. In fact, this notion, I think, is also due to Newhouse, a homoclinic class of the periodic orbit. Okay, and what we prove is that for every ergodic measure of maximizing the entropy, okay, there are periodic orbits such that the support of the measure is exactly this compact set defined in terms of the periodic orbit. Okay, and then what we can couple with the David Burger's result. And since here you have a compact invariant set, okay, actually, and we know that it has the entropy, it has topological entropy equal to the full topological entropy because it carries these measures. Then we can apply some version of David result. And here we will know that, okay, David Burger proved that all accumulation points are MME, but inside this set, we proved that there is only one MME. So the measure that described the repartition, the distribution of the periodic orbits have to converge toward this measure. Okay, so you saw the question coming. Okay, now, in principle, well, as long as you don't intend to do it yourself, you can imagine, okay, I have a periodic orbit, very good. I can compute the local stable, the local unstable, and then I can extend them applying the dynamics, and I will find intersections. Okay, and I can apply the dynamics more and more and get more and more intersection. And if I believe in this result, this intersection in the limit, they feel they are dense, they are contained in the homoclinic class, so in the support of the measure maximizing the entropy. And yeah, they are dense in it. Okay, so this could be a way. Then you have to decide in what order you compute them. And then, okay, will there be some convergence? Okay, so this is the main question. Okay, why would I be interested in finding the support of the MME and okay, and this whole the hyperbolic periodic orbit related to it? Okay, it's because of the following question. So we are looking at surface diffeomorphism. So a rough idea, which is true up to some point, is that there should be some parallel, some dictionary between these and smooth interval maps. Okay, for smooth interval maps, you can localize their ergodic measure maximizing the entropy using the renormalization intervals. Okay, this is essentially, each time you have an MME for an interval map, you will find that it is contained in some renormalization interval, some periodic interval, which might be the whole interval if there is. So there is always one. And then it doesn't contain a smaller, it is all the support will be all the points that that are inside one periodic interval and whose orbit does not fall into a smaller periodic interval or renormalization interval. So you have a kind of tree structure that organize the MMEs for an interval map. Okay, you have the renormalization interval. Okay, you can, okay, they are not exactly disjoint or nested, but almost. So you have this kind of, okay, so let's pretend they are like that, disjoint or nested. So you have a kind of tree of these intervals, and essentially what you know is that they cannot be very deep. The MME have to live somewhere in this tree. Okay, so these intervals, these periodic intervals, they give you a kind of separation. Okay, the MMEs for interval maps, they are usually sometimes either the support is a union of interval, or it is something like a counter set. Okay, and then even if it's a counter set that comes from looking at a union of interval and excluding the points that fall into a smaller union of intervals. Okay, so they are really related to something nice that you could try to find out. I mean, you could, if you have an interval map, you can start looking for periodic intervals, well, at least theoretically. And then it would give you this structure, and then you have to compute the entropy of these points that are in some renormalization interval, but not in the smaller one. Okay, what we know is that this quantity will go to 0 for a C-infinity map when you go deeper and deeper into these renormalization intervals. Okay, and one question is there a similar structure for surface diffeomorphism? Okay, this is not what we do. Okay, what we do is that the measures are related to periodic orbits for some reason, essentially by Pearson theory, and the fact that we are in dimension 2. So you have a lot of, you have a consequence of Pearson theory is Katok horseshoe theorem that tells you that if you have a measure with no zero Lyapunov exponent, then you can approximate it by a horseshoe. This horseshoe has lots of periodic orbits. It has a whole lamination, stable and unstable lamination. Okay, so when you have a measure with a big entropy on a surface, it comes automatically with a lot of stable and unstable stuff. And one very naive thing that you can do is, okay, you know that at almost every point you have this stable and unstable that accumulate. This gives you bunches of curves in two transverse directions. Okay, then you can, if you have curves that are in two directions, at least very locally, you can draw little boxes. Okay, this is because, okay, why does it work? It's because 2 is equal to 1 plus 1, which I will not prove. And this is a bit stupid, of course, but it's what allows us to relate. Now, when you have your measure, which is quite abstract, you can enclose it into this type. Okay, we call it quadrilateral because they don't have any. So let me draw a stupid picture. Okay, so this is something like this. So let's say this is the stable, this is the unstable. Okay, and each time you have typical points for your measure, around them they have lots of stable and unstable manifold. And using Katok horseshoe theorem, you can actually use not the measurable foliation of Pearson, but those related to a periodic orbit. Okay, so essentially, you start with, you have your measure. Okay, maybe it's some contour set. Well, this is not great visualization, but then you can cover it by these type of things. Okay. Okay, with small diameter, as small as you want, just because you know that, in fact, you have, at small enough scale, you have lots of stable and unstable. Okay, they are measurable, so it means that excluding a set of small measures, they depend continuously, so you can get a picture like that, and then you can use Katok theorem to replace the one that comes from this measurable structure by the one related to a given periodic orbit. Okay, so what's the thing is that instead of having now, what you do is that you can do this almost everywhere. Okay, so you can cover, let's say, 99% of the measure with these quadrilaterals. Okay, and now what do you want to do? You want to prove finiteness, for instance. I mean, you want to see where the, so what will happen is that if you take another measure, you can do the same picture. So if this measure were too close together, okay, you would have intersections between stable and unstable. Okay, then you have to find some reason to show that these intersections are transverse. And then somewhere in the proof, we show that if you have this, you have this transverse intersection, the measures must be the same. Okay, so what do I want to say from this argument is that, okay, it's like a very, very messy counterpart to the renormalization intervals. So on the intervals, we had this nice structure where we could say, okay, you have these intervals that are well defined without speaking of the measure. They are just periodic intervals. Okay, and the measure each measure sits inside one cycle of interval, and there is no other measure that is exactly inside the same. Okay, the other measure must be outside, or if they are inside contained in a smaller cycle of intervals. Okay, so here we don't have this, we don't know actually, in fact, that we have this kind of cycle related to the MME. We just have this messy picture. Okay, but maybe, so one thing that you could imagine is that if you're able to see where the MMEs are and what these homoclinic classes look like, maybe, well, maybe you don't understand anything more, but maybe you would see something. Okay, so I don't know. It's otherwise, okay, if you don't, so this is kind of motivation. Another thing that you might want to be interested is we know this measure is finite. This number of measures of ergodic measure maximizing the entropy is finite. We know that the number is something reasonable. Okay, it's semi-continuous. Okay, if you are able to approximate these homoclinic classes in a reasonable fashion, then probably you can prove upper bound on the number of MMEs. Okay, so I'm here to ask a question. So that's, so how long do I have? Good. So the newest result is that we have, so again, continuing our work with Sylvain Crovisier and Henri Sarig, Okay, we are finishing writing. So in the same setting, we establish some property which is related to a spectral gap. Okay, unfortunately, this spectral gap is for the symbolic system. Okay, so there is a statement. In fact, for the symbolic system, this relies on a result of Van Sier and Omri-Sarig, okay, where they show that some natural property of the so these are countable Markov shift, that is like subshift of finite type, but with infinite alphabet. And so you have these non-compact SFTs. They can be bad to some extent, but you have a class which is especially nice, which is called stably positive recurrent by Gurevich in the 70s, and was rediscovered and generalized by Omri in the years 2000, 2010, under the name of strongly positive recurrent. So these are really so there are a lot of good properties that make them quite close to the compact case, the classical case. And in fact, so in this paper by Van Sier and Omri-Sarig, they show that this property is exactly equivalent to the existence of a spectral gap for some reasonable, they have a definition of reasonable Banach space in this setting. So once you have this spectral gap for the symbolic dynamics, we show that okay, so the first thing is to see, this is the key thing is to see that in this setting, it forces the Omri's symbolic dynamic to be SPR, to have this spectral gap above, and then we have all kinds of nice statistical result in the symbolic setting, exponential mixing, central limit theorem, almost sure invariance principle. I mean, the comparison with the Brownian motion, all with respect to Holder observables. And the coding is good enough so that everything goes down for the surface. Okay, and so this is why I put these questions before about rate of convergence. Okay, because here, okay, you have the exponential mixing. This is definitely a rate. Okay, you have a lot of stuff. So maybe these results contain some things that could help with the previous question. Okay, so fantastic. We know a lot of things about MMEs for this non-uniformly hyperbolic situation. I mean, just infinity smooth on compact surface with positive topological entropy. We have repeated a large part of the theory of the uniformly hyperbolic theory, but okay, have you seen one of these measures? Well, I must say I have not. I mean, I have in some trivial cases. So I would like to see them. Is there a way to sample them? So of course, I mean, there is this. If we had a nice transfer operator on the manifold, on the surface, okay, probably it could help. I mean, there is this a paper by Sébastien and Carlangelo that does a fantastic thing for the Anosov case. And then there are further works for in the uniformly or piecewise uniformly hyperbolic setting. Okay, how could you use them to estimate the MME? So I don't know already in this situation if it is reasonable. Okay, then here I don't know if it is defensible. If it is Anosov, yes. If it is axiome, no. Axiome, you see smell horseshoes, everything happens inside a disk. You can put it everywhere. So yeah, that's in general, that's a good question to understand what are the sources of entropy. I mean, you have, as you said, this global reason, and then you can also have like horseshoes at very small scale. And maybe there are also other phenomena that I don't know. So yeah, here we don't know that it is related to. So yeah, so okay, so this is these are the questions that, in some sense, I ask them because we are here. I mean, I'm not very optimistic, and I think it still requires a lot of theoretical work, and probably also something quite difficult to implement. Okay, so now you can say maybe, okay, let's see if it's too difficult, but let's do something completely different. Okay, so here, what we are doing, okay, this is something I did some time ago, actually. And you take two quadratic maps. So this is on a surface, but it's not a diffeomorphism. It's not invertible. You just have essentially the product of two quadratic maps. Okay, there is a mistake. It's 1 minus a times x squared and 1 minus a times y squared. Okay, and so you have two quadratic maps with close to being full. Okay, and you add some coupling between the two. Okay, and you do it in a symmetric way for some reason. So you can iterate forward and you get something that you might hope is the absolutely continuous invariant measure. Now you can iterate backward. What does it mean, iterate backward? Okay, it's not completely clear. I mean, for me, you have essentially you have either 0 or 4 preimages. And essentially, you try to pick one randomly. Okay, you have to be a little bit careful. So you pick randomly, but not among the 4 preimages. But you look at these preimages and you make sure that they have also preimages. You only consider those who have preimages. So maybe you have 4 preimages that have preimages, but maybe some of these 4 don't have preimages. So there is some quirk here. And now you iterate backward. Okay, and you get something that looks very different. I mean, I think the support is the same. I mean, the visual support is the same. And okay, so there are some result, I mean, very old result by Le Drapier about the case of the full shift, which suggests that this might be an equilibrium or essentially a G measure for those who remember from their very youth what it was. It's equivalent to being an equilibrium. But I don't know. I mean, it's especially because you don't always have preimages, it's not clear. Okay, so why do I speak about it here? Okay, first because I like this picture, even though I don't really understand it. And also, okay, when we had this computation of the intersection of the stable and unstable. One way to put some ordering on it is to do something like this. Now, if you have a diffeomorphism and you want to think about something that would be non-invertible, one reasonable thing would be to try to quotient by the local stable manifold. Okay, so at some level of, at some ideological level, this is not completely unrelated to taking pre-images for the map. Okay, you might not agree, and I have no better argument than what I said. So anyway, it gives you this nice picture, which looks very different from the forward thing. And this is, well, maybe you have some answers. I don't really have. So in the meantime, thank you. That was effective.
So if I give you a very nice explicit map in 2 dimensions, say the standard map, very nice. Do you have a way to plot the measure of maximal entropy you expect, even a heuristic one, starting from hyperbolic orbit and intersection?
So, yeah, so, okay, you have to make sure that you have a horseshoe somewhere so that you have positive topological entropy.
Standard map,
That's
it's fine.
known, yeah. And then, yeah, I mean, for now, the thing would be to look for periodic orbits to eventually put some lower bound on to compute exponents. I mean, so it's conservative, so probably you just need to compute the norm and see that it doesn't, it stays away from 0. I mean, maybe there are lots of periodic points with very small exponent, I don't know. And then try to see where are those guys. And I hope you wish me luck.
No, it looks very heavy from a computational point of view. If you need to locate, it's very different from the SRB measure where you just pick a point at random, you iterate it, and you look at what you see.
Yes.
So it looks so much harder.
Yes. This is why I wrote this to have to be able to show something. So, yeah, I mean, the other possibility is to, okay, so you have to find a good, well, you can start, even if you don't know if it's a good, you can start with a good periodic, with a hyperbolic periodic orbit and try to compute essentially the homoclinic tangle. I mean, this stable and unstable manifold, starting locally and then iterating and see if it feels in some nice way.
And so as far as you know, there is no existing picture for the standard maps.
No, I don't think so.
Other questions?
Thanks. So you were talking about 2-dimensional C-infinity diffeomorphisms. Is it so? I mean, often as a sort of simple model for studying those, people like to look at 1-dimensional maps. Do any of the things you say for 2D, are they likely to kind of carry over through to 1D?
Okay, so for 1D, well, if you're expanding, I think it's much easier. I mean, there you have a well-known transfer operator, and so you can, you should be able to do stuff.
But like, say you have a quadratic map or something like that.
So I don't know, you could try to understand something like that. So I should say that this idea of that you pick a point at random and you iterate backward, choosing randomly between the pre-images, it was used and then justified for, let's say, rational maps on the complex plane, on the Riemann sphere. There it is proved, it's not very difficult, well, knowing all that people know about these things, that it converges to the MME carried, which, yeah.
Yeah. Okay, but I mean, I guess here it's not Markov, but I mean, so maybe it's not like it's like the conformal measure, but you also need it's not invariant. But if you go back to the previous before.
Yeah. So another thing that you can do in one dimension for interval maps, I mean, for expanding, let's say, circle maps, is use the symbolic dynamics.
Yeah.
Because then you have explicit. I mean, it's easy to compute, and you know what I mean. You just have the uniform measure on the symbolic dynamics, and so for more generally, for if you just take a unimodal map or a quadratic map, you also have. So I'm not sure what is the good way to do it. One thing that you can certainly do is there are also good symbolic dynamics going back to Hofbauer that tell you, okay, that have some explicit construction, and also they have this property that at infinity there are very few, let's say, very few loops. So they have this exponential approximation property. So I'm not saying it's completely easy, but it seems more reasonable, yes.